Hello friends, I welcome you for the lecture on BJT Differential Amplifier. Now, differential amplifier is also called as a difference amplifier. So this differential amplifier is an very important block diagram, or I can tell like building block in an op-amps. Now we discuss more about differential amplifier in this video. A difference amplifier has two inputs, so as shown in the figure 1.40. It has two inputs, V1 and V2, and the output is V0. So if we can see the output equation from equation 1, V0 is directly proportional to the difference of the two voltages V1 minus V2. So it is very simple that the difference voltage V0 is directly proportional to the difference of the two voltages V1 minus V2, and the proportionality can be removed. The proportionality can be removed with the differential gain. So V0 is equal to A suffix D, where A suffix D is differential gain times V1 minus V2. So it is shown in the equation 2, where the output equation V0 is A suffix D times V1 minus V2. Now actually this is an output equation where equation 2 is an ideal equation of a differential amplifier or a difference amplifier. But in practical its working will be different, where it also has some part of a common signal being added to it. Now we learn that in deep. Now we can see that in equation 3 it is known that if V1 minus V2 is taken as V suffix D, that is difference voltage, then the differential gain is output by the difference gain, so that is like V0 by V suffix D, and it can be calculated, that is the equation 3 can be calculated like an integer value. If we want to calculate the differential gain in terms of decibels, we apply logarithm to the equation 3. So the differential gain in terms of decibels will be like 20 log base 10 of AD, as shown in equation 4. Next, we go on with another topic called as common mode gain. In common mode gain, what is common mode gain is that V1 and V2 actually has some common signals present, and in the output it will be replicated. So the common mode voltage is like V suffix Cm, that is V1 plus V2 by 2, as shown in equation 5. So I repeat, V suffix Cm, that is the common mode voltage, is equal to V1 plus V2 by 2, as shown in equation 5. Now if there is a common mode voltage, the output voltage will be like V0 is equal to common mode gain. Now the common mode gain comes into picture, so the output voltage will be like ACM into VCM, as shown in equation 6. Now the total voltage, if we can see, of a differential amplifier, that is V0 is equal to AD plus ACM into VCM. So actually the practical differential amplifier also amplifies the common mode gain. That is one problem, or it is a practical difficulty with the differential amplifier. So when we define a differential amplifier, we make sure that the common mode voltage is less and the difference voltage is more. So now actually to go in practice, we have to decrease this common mode signal. So we are going with the next topic called as common mode rejection ratio. So we try to have like rejecting the common mode signals, so it is termed as common mode rejection ratio. So we just see what is common mode rejection ratio. So common mode rejection ratio in an abbreviated form we write like CMRR. So if we want to define, we can define CMRR as the ability of a differential amplifier to reject the common mode signal. Right, I am repeating it. The ability of a differential amplifier to reject the common mode signal is called as the common mode rejection ratio. It is expressed as shown in the equation 8. So common mode rejection ratio CMRR is modulus of AD by ACM. So it is the ratio of differential gain to that of the common mode gain. CMRR can be calculated in terms of decibels, so it is like 20 log base 10 of AD by ACM. Now the total the output voltage in terms of CMRR is written mathematically in the equation 10. So equation 10 lets us to find out the output voltage in terms of the CMRR value. Now we go on with the features of the differential amplifier. If we see the differential amplifier features, the first feature it has that it has high differential voltage gain. So it has high differential voltage gain, that means A suffix D is very high, and it has low common mode gain. So we have to do that. So usually when we design a differential amplifier, we have to reduce the common mode signals, so eventually we have the low common mode gain. And another important point is that it should have high input impedance, low output impedance, and larger bandwidth. Now if we can see the operation of the differential amplifier by using BJT. Now the figure 1.41 shows the basic BJT differential amplifier with the two transistors connected. So the two voltages VB1 and VB2 are connected to the transistors Q1 and Q2, and this Q1 and these transistors Q1 and Q2 are biased with the voltage DC supply voltage V plus. And here we note that the two collector resistance are same, so it has to be notified that the same resistance has to be taken, RC and RC, the two, that is for the transistors and Q1 and Q2 both should be like the same resistance RC. And another point is that both the transistors should be in the active region. Next, now if we can see, now our ultimate aim is we try to eliminate the common mode ratio. So wherever the common mode ratio, we try to just decrease that common mode ratio. Now if we can see the common mode operation, so here the circuit is considered in the figure 1.42, where the common mode voltage is taken as 1, okay, and we calculate the difference between the V1, and that is the output between the two transistors Q1 and Q2. Now if we can find the current in the in the emitter of the first transistor IE1, and it will be the same as the current in IE2. So IE1 will be equal to IE2, that will be like actually IC by 2, where IC by 2, we know the equation, IE is approximately equal to IC. So IC here has been written as IQ by 2, right? So now the equation of VC1, if we can just see that that is the output at the collector voltage VC1 is V1 plus that is the voltage actually V plus minus IQRC by 2, right? And when we apply the KVL on the first transistor, we have an equation VC1 will be like V plus minus IQ into RC by 2, which is shown in equation 12. And similarly the equation VC2 can be found, and then if we just we subtract, we get an equation VC2 minus VC1 as 2 times the del I, where it is a change in the del I value in terms of the that is the collector resistance RC. Okay, now this is about that differential mode. Now if we can go with another topic called as the DC transfer characteristics. So we see the DC characteristics of the transistors, so we can try to calculate the collector currents IC1 and IC2 as shown in equation 14 and 15, and then the total current of the base, that is like the total current of the collector IQ is equal to IC1 plus IC2. So equation 16 shows the total current, and if we just have a ratio of IC1 by IQ, so we get one ratio, and we can see here IC1 by IQ we get equation 17, and the IC2 by ICQ we get an equation 18. With these equations we just draw the transfer characteristics of the differential amplifier. So the characteristics of the DC differential amplifier is shown like in the figure 1.44. So that is about the BJT differential amplifier. Hope you understand the basics of the BJT differential amplifier, and thank you for watching this video. Thank you.